So let's continue. So in last slide we saw that in vector form we have this L2 norm, which is nothing but dot product of vector with itself, and in signal terms we can say that it's nothing but the integration of signal. Okay, so it's nothing but inner product of signal with itself. So here both is v of t and v of t, and here it is conjugate. So we know that this will be vt of mod square, and this term under the under root is nothing but our energy. So these are some advantages of representing vectors in terms of signals. So now I think we are ready to move towards Gram-Schmidt process. So let's start. So what Gram-Schmidt said is that any set of m energy signals, I am just repeating, can be represented as linear combination of n orthonormal basis functions, where n is less than or equals to m. Right? So we will derive this thing with an example, and for that we will be taking a step-by-step procedure. So first number is step number one. Step number one, let's consider, I am not writing directly the equations. If you will find uh, some books, then you will find that they will directly write some equations in general form and they are confusing at first sight. So I am not writing that thing. I am just starting with signals directly. So let's say, let the first signal is S1t and its energy is E1. So the first orthonormal basis. Okay, so what is our aim? Firstly, let us just generalize the things that our aim is to write. Let's say we have three signals. So our aim is to write all the three signals in terms of, let's say, A phi 1 plus B phi 2 plus C phi 3 and so on. We will see how many phi 1 phi 2 are required. Okay, how many phi's are required, that is how many orthonormal basis functions are required, right? Similarly S2 we have to write in terms of phi 1 phi 2 and phi 3, and similarly S3. And if we have n number of signals, we have to write all signals in terms of this, provided these are orthonormal basis function. Orthonormal means that these are the signals with unit energy and we know what is basis, right? So our target is to find phi 1 phi 2 and phi 3, that's it, right? Whatever is required. And as we said, our n is always less than or equals to m. So if we have three signals, then our orthonormal basis function will always be less than or equals to 3, and this point we will see, right? So we already know that our n is less than or equals to m. I specified this. Okay, so please mind this. Now phi 1t is directly given by, I'm just writing t, S1t divided by E1t. Now how I directly wrote this? Because we know that if we divide S1t by its energy, because E1 is the energy of our S1t, then this phi 1t will be unit energy signal, correct? So what we want? We want this as orthonormal, that is, it should be having unit energy, right? Now how to verify that this will be having unit energy? We can directly verify, just we can calculate the energy of this, right? So we can directly calculate phi 1t energy. So how we will calculate energy of phi 1? Simply minus infinity to infinity phi 1 square t dt, and it's nothing but S1t upon E1, right? And we know that E1 is constant, we can take it out, and this integral with dt, I forgot dt, is nothing but E1 only. So E1 will get cancelled, and at the end we are left with 1. So we can say that our condition is satisfied, that this is our orthonormal basis function. Now basis function means that when we will find phi 2 and phi 3 and so on, then this all should be orthonormal, right? Orthonormal means that they should be orthogonal to each other mutually, as well as they all should be having unit energy. Okay, so this is our aim in each and every step. Okay, now I am just writing a quick note. A note is that this is not needed right now, but I am just writing that basis functions are not unique. And it depends on the order, or we can say on the order in which orthogonalization is performed. Sorry, my bad, is performed. It depends on this, right? Now step number 2. Let's continue our journey. Now, as I said, our main aim is to obtain F2. We have to find, sorry, phi 2, and this phi 2 should be orthonormal, that is, it should be having unit energy, and it should be orthogonal to phi 1 as well, right? So how we will do this? Obviously we have to use S2 energy signal. So this step might be confusing for some of you. What I am doing is that any signal, as I said, that just always try to compare with vectors, that any vector v can be represented in terms of a I cap plus b j cap, or in vector space a v1 plus b v2, right? Same thing I am doing over here, that with some constant s22 I am representing it in terms of phi 2, and with some constant s21 I am representing it in terms of phi 1. Now as we know that since phi 1 and phi 2 will be orthogonal, we don't know that, but we want this, right? Since phi 1 and phi 2 will be orthogonal, right? So we can write, this will be the basis. Right now we are assuming that phi 1 and phi 2 are orthogonal, but we will verify after finding phi 2 that this is orthogonal to phi 1. Actually we will find like that. Okay. Now you might ask, what are these S22 and S11? S21. These are scalars, obviously, like this. Here we have A and B. But what are S22 actually denoting? The same thing, the A and B are denoting. What S22 denotes? S22 denotes the projection of S2T on phi 2. I hope you can compare that. What A denotes? A denotes the projection of A on x-axis, or here we can say on V1, or here we can say on x-axis, and B denotes on y-axis. That's it. So this is projection of S2T on phi 2T. Similarly, now you can guess for S21. What is S21? Just let me put this aside. So what is S21? S21 will be projection of S2T on phi 1T. Simple. Now our main aim is to find, just let me put this back, that our main aim is to find phi 2T. Please don't forget this, right? So how we will proceed? So let's start our journey, that from above equation, if someone will say that just make phi 2T as subject, then we can write this directly like this, that right upon S22. But using this equation you can never find S2T, sorry, phi 2T. And why it is so? Because obviously we know S2T because this is our signal, it is given in our question, right? We can find phi 1, we already know phi 1T. We can find S21 as well, because S21 is nothing but, let me write just that projection is nothing but our dot product. So it is integration of S2T into phi 1T. I can't say dot product, let us say inner product, it will be better. So this we can also find, because we know S2T, we know phi 1T, we have to just multiply them and just we have to integrate. But what about S22? How we will find this? Because S22 is already in terms of phi 2T, because it is defined like this, inner product, right? Since we need to find phi 2T and S22 is also in terms of phi 2T, we can't find phi 2T using this equation. So we need to change our approach, right? So we need to change our approach, and the approach will be that define an intermediate function. Define an intermediate function, let's say g2t, some book denotes it by gamma of t or something, right? But I am denoting as g2t by, I am just writing this thing, that it will be s2t minus s21 into phi 1t. Now if you will carefully observe, you might wonder that what I wrote this. But if you will carefully observe, what I did is I just subtracted S2T component on phi 1T, that's it. That is whatever S2T's projection is there on phi 1T, right? I just subtracted it. And if I will subtract this, then what I will get, let's see, let me just not go in deep into this. So now we have G2T, right? Now we need to verify that whether this G2T is orthogonal. First let's verify for orthogonality and then we will normalize it by its energy so that we will get orthonormal. Okay, so first let's discuss about orthogonal. So let's verify that if it is orthogonal, because at the end what we want phi 2t, right? We will calculate phi 2t from G2T, but we know that phi 1 phi 2 should be orthogonal as well as orthonormal, and orthonormal definition says that it is orthogonal in itself and in addition they have unit energy as well, right? So let us verify this. So how will verify? Simply a dot product, my bad, inner product, okay, because we are in signals now. So just we will replace G2T. So if I will replace G2T, what we will get? Minus S2151T, and this is in multiplication with phi 1T dt, right? Going to next page, I am just separating both the integrals, that integration minus infinity to infinity S2 of t phi 1 of t. I urge you to derive this so that you can get clear idea. Then S21 phi 1t into again phi 1t, right? I am just opening the brackets, that's it. We know that this is nothing but S21 and this S21 is constant, so taking outside we are left with phi 1t into phi 1t. So I am just writing phi 1 square t, and we know that this is our orthonormal signal and its energy is 1 and this is nothing but its energy, so this will be 1. So at the end we are left with S21 minus S21, which is 0, and we verified that our G2T is orthogonal to phi 1t, and this is intuitive because at first glance this equation looks quite a bit difficult, but it is not difficult because we have subtracted S2T, okay, its component on phi 1t, right? So there is no component of S2T on this phi 1 axis, right? And that's why G2T is orthogonal to phi 1t, right? Now we are somewhat near to our aim, that at the end what we want phi 2t, right? So we verified that G2T and phi 1t are orthogonal, but G2T is not having normalized energy, that is G2T is not orthonormal. So we need to normalize its energy to 1, right? And let's denote that by phi 2 of t, which is our aim, that it's nothing but G2T and divides by its energy, and we know that how to find the energy, right, from our previous videos. So that's it. Now let's calculate the energy of G2T, right, because we need to calculate at the end this G2T so that we can get phi 2T. So if we will calculate this, then I am just continuing this step, that integration, I am just not writing under root. So G2T, as we know, it's S2T minus S21 phi 1T, its whole square, and dt, right? I am opening the brackets. So we know that how to solve this. It's a square plus 2b plus b square. So I am just writing quickly just to save the time. S21 square phi 1 square t dt and minus 2ab. So S21 S2t phi 1t and dt. So at the end, just separating integrals, we are left with S2 square t dt then second term will be just separating integrals. Okay, this you can solve it easily. It's just simple opening of square bracket. So s21, and this is the middle term, so my bad, it's 21, and this is s2t into 5t, and of course dt, right? This is nothing but, let me change the color, this is nothing but energy of our s2 signal. Let's denote it by E2. This is nothing but s21 square, right? And because this will be 1, right? s21 is constant, so it will be outside, and integration with this f1 will be 1, right? And this middle term will be written as twice s21, and this is also the definition of s21, right? So we have s21 square. So at the end we have E2 plus this thing minus 2 times of this thing, which is square. So we are left with minus s21 square. So at the end we are left with E2 minus s21 square. Sorry, let me write here that it's E2 minus s21 square. This is the energy of our G2 signal. So let's take under root, right? Of course, this is the energy of our G2 signal. So we will substitute it here, right? So what we get at the end, because at the end we want phi 2, so phi 2 will be G2t divided by E2 minus S21 square, right? Now can you similarly find phi 3? Yes, so let's try quickly. So step number 3, again the aim is to calculate phi 3 of t. And how we will calculate? Phi 3 of t will be given by the same thing, G3 of t. Now I am not going into further details because I am going to generalize this now, right? And obviously what is G3? Now can you write G3 alone? That G3 is nothing but, take just SC3, then subtract its component from phi 1 axis and from phi 2 axis, and this will make G3t, okay, orthogonal to both phi 1 and phi 2, and at the end G3t is related to phi 3t with this relation. So at the end we can say that phi 3t is orthogonal to phi 1t and phi 2t, and since we normalize this, so we can say that all these three are mutually orthonormal, correct? So I am generalizing that in general I write GIT as SIT minus summation of j equals, this is just a general form which all books write in the very beginning, but I am writing at the end. And what is phi IT? Okay, you can easily generalize this thing, and you can write it as integration of gi square t dt, right? So this is a generalized form of our orthogonal Gram-Schmidt process. Now let's consider example. At the end we have to solve the examples, right? So let's consider 4 signals.